All right, so it's just after 2 o'clock Eastern time. We're going to get started. Welcome, everyone, to AMS Weather Band's latest webinar, Understanding and Predicting Northeast Snowstorms, a Lifelong Journey. If you have questions during this webinar, please put them in the Q&A. We will have specific time for questions after the presentation. Our speaker today is Dr. Louis Uccellini, recently retired as the Director of the National Weather Service. Dr. Uccellini served as the 2012 president of the AMS and served as a director of NCEP, the National Centers for Environmental Prediction. Dr. Uccellini, thank you so much for joining us today.
Well, thank you, Eric, for having me here. And thanks to everyone who's joining up to listen to this. I just want to start off by saying that, like many of you who are listening in, my journey in meteorology started with my deep interest in snowstorms. So I figured I would go through this to illustrate not only the love that we all have for these types of weather events, but also the advances that the entire enterprise, in fact, has made in terms of our understanding and ability to predict and influence decisions for public safety in the face of these snowstorms. So if we go to the next slide, Eric. So as far as an outline, we'll start with my initial interest. I do want to focus on the transition zone in terms of the increasing importance of numerical models in influencing our forecast capabilities. So we'll look at that era in the 1970s to the 2000s. The forecast improvements that we've been making recently, the effort within the Weather Service, and now the entire enterprise to work together to build the weather-ready nation. Thought I would bring this all together with the abilities and performances during the 20 to 24 January 2016 Northeast blizzard. Ongoing opportunities, as we like to look at them, and challenges. And then we'll end with a reflection, taking me back to my roots, and then a summary. So next slide, please, Eric. So I started early in meteorology. My interest in weather, I think there are a number of us that can remember as far back as they can remember their interest in weather. And for me, it was snow right from the beginning. And my parents often said that I started talking about snow when I started talking. And that's going way back, folks. I got excited about every snowstorm. I got excited about snow. I even got excited about snow flurries when I was really little, and wondered how that happened. Okay, that your world could change in front of you with a snowstorm, especially. I also remember Carol and Diane as they came up the East Coast in the mid-50s, and was particularly influenced by Hurricane Donna, which came across Long Island, where I grew up. In fact, actually made landfall pretty close to my hometown. I was always fascinated by the forecasting aspect of snowstorms and how it could be raining on Long Island and snowing just north of New York City. I mean, it just absolutely fascinated me that we were that close to a snow event and still not getting it. Was always anticipating a snowstorm when there was any kind of chance. The 4 inches or more was the signal from the Weather Bureau at the time that this could be a heavy snow. That was as far as they went with accumulations. A lot of times that did not happen, and those are the cases for profound disappointments. That's me in a March storm, and we used to have March storms on Long Island back in 1956. All right, next. So I should say that the winter of 60-61 was what really locked me into meteorology. Paul Cosin and I wrote a snowstorm monograph, Northeast Snowstorms, that's published through the American Meteorological Society, and came up with a ranking, Northeast snowfall impact scale. So we could rank the storms that we reviewed that actually covers most of the 20th century. And you see the storms in 1960-61 rank in the top 26 of those storms. And especially interesting is the 1961 storm, the February 2nd through 4th storm, that really made the impression on me that this is amazing. As we go to the next slide, please. You see from the analysis that was provided in the monograph, this storm came in with very cold air up front on February 3rd, 7 a.m., woke up to 4-degree temperatures. So remember looking at that thermometer and thinking there's no way this can go over the rain. And the thickening sky already coming in. It's the first time I heard anybody say this red sky in the morning, sail or take warning. Turned out it's my father, sort of lending his confidence that this could be a big one, as he noted that when he woke up there was this red sky and to the east. And you can see how this storm developed. It's a classic, what was called at the time a type B storm with the secondary development along the coast and then moving on up. If we go to the next slide, please. The snowfall totals were in the 2-foot range in Western Long Island. We got about 20 inches in Bethpage. We did have a brief period where it went over to rain about 5 o'clock in the morning. And all that did was put enough ice on top of the snow that you could actually walk on the top of this snow cover, which also involved a number of the snow events in middle to late January that preceded the storm. It was a very cold period, almost 2 weeks straight where the temperatures did not get above freezing. So this was a very impactful storm with this kind of snow cover. I should note that Paul Cosin is the lead author on that monograph, and these are his analysis, both of the surface pressure that we just saw and the snow cover here. Okay, next, please. Nice picture from the Bell Parkway, and as you see, even though there was a forecast for a heavy snow, people tended to wander out as the storms were developing, and in this case, major traffic jams and snow clogged the streets that basically shut down the city for 4 or 5 days. It took about 5 days to clear out not only the main roads, but the city streets as well. Okay, next, please. So from a forecast perspective, in what I was growing up in was, it was pretty hard to get an indication from the official forecast more than a day in advance as to whether there'd be a possibility of a significant snow event. George Cressman, who was one of the developers, one of the pioneers in the operational modeling systems that the Weather Bureau was actually started working on in the 50s and 60s, put this out in terms of this level of predictability of these types of extreme events, that even with the modeling that had been done up to 1970, which is over a decade, the predictability of heavy snow was in that 12-hour range, and at scales that don't lend itself to differentiating what goes on Long Island versus New York City or the lower half of what we always termed upstate New York. These types of storm systems pose significant prediction challenges through the 50s and 60s and even into the 70s. In fact, if we go to the next slide, there were those in the community who felt that given the inability to predict weather features like secondary coastal cyclogenesis, that we should abandon the use of numerical models in research that uses weather sequences for deduction about the real atmosphere. This was written by Ramage in the BAMS, in the Bulletin, in January 1976. Just as I was working on my first model as part of my PhD thesis. I can tell you when this paper came out, there was a lot of stir amongst the students and professors in terms of this type of attitude that the models were not capable. We were not capable of actually simulating these types of systems, and of course being able to predict based on those simulations. Okay, next please. So as we worked our way through the 70s, some interesting things happened in terms of those models. We were not running global models at the time. We were running hemispheric models, and we were running finer resolution, limited fine mesh models, the LFM as it was called. One of the big early successes with the use of models was this famous 5 through 7 February 1978 blizzard. I should point out that I was at the University of Wisconsin at this time, so I missed this storm. But I can tell you, we were following it every step of the way, given, as we'll see in the next slide, we can go to the next slide, please, the forecast for the storm. Should note that this storm did obviously spun up into historic proportions. That's over 30 inches of snow there that's centered right over northern Rhode Island into southeast Massachusetts. And there are a number of people who I am sure that this storm locked them into a meteorological career, much like the February 61 storm locked me in. I know Jim Cantori talks about this. You all know him from the Weather Channel. Michelle Minnelli, the National Weather Service. She worked her way through the Hurricane Center as the first woman hurricane specialist. And Jason Toole, who's the current Eastern Region Director, who has a number of forecasters who have to deal with these storms. And Eastern Region covers this area and more, up to the tune of about 100 million people. So it's people who are very busy today in building off all of our improvements in the models actually were influenced by this storm. Okay, next slide, please. What was interesting about this is from a medium range perspective, 3 days out, the models were forecasting the storm. And this is something I remember very clearly being at the University of Wisconsin and wondering if we should fly. There was a group of us there from the East, whether we should fly back home and get ourselves positioned for this storm. A couple of tests that were being given at this time kept us in school. But it was amazing to watch the models work their way towards the actual event. As we go to the next slide. In this slide, we have the forecast of the surface on the top, those top set of panels, and the 500 millibars and the surface, sorry, on the top, and then the analyzed on the bottom. And you can see from an upper air point of view, an incredible trough that was digging into the eastern third of the country was predicted to generate a very significant storm off the East Coast. And this was something that we were keyed in on. And then when this LFM model locked in at 48, 36, 24, and 12 hours, as we approached the storm, it was pretty consistent in this forecast. And this was really, I believe, the first time that the models consistently predicted a storm like this, and especially a consequential storm like this. This was actually written up by Dave Olson and a team from NMC, and it was really touted as sort of a period that we were now entering, this new period of model prediction for these types of storm systems. And it's certainly, when we reflect back on the Ramage quote from just a couple of years before this about abandoning the models, this was sort of a stake in the ground that we're on to something here, folks. Okay. All right. So we'll go to the next slide, please. Now, that was the good news. The bad news was that many people that lived on Long Island, Southeast New England, didn't really believe the forecast. And the reason is that there was a storm just before that, the famous Cleveland bomb that developed over the Ohio Valley and produced a major snow event, blizzard conditions in the Great Lakes region, was initially predicted to move up the East Coast in that 4, 5, 4, 3, 2 days in advance. And it actually was one of these storms that really amplified and moved up actually right over the Appalachian mountain chain. So now, several days later, you got this. And when people woke up, it wasn't snowing on Long Island or Southeast New England. And I believe the forecast had that the snow would start earlier in the morning. So there was a delay. So people decided to go to work. And this is what happened in near the Boston area in terms of the getting stuck, trying to get home. And of course, when you have roads that are clogged up with cars like this, it's almost impossible to open up in real time. So it takes days to open up these types of road systems. So there was chaos and cars, buried in the snow. And we used that, Paul and I used that as a cover on the first smaller monograph that we wrote and published in the early 90s. And this is apparently a very famous picture for those who lived through the storm in eastern New England. Okay, next slide, please. So, so working off of that success, we come into 1979. I moved from Wisconsin now to Maryland and joined up with the newly formed Goddard Laboratory for Atmospheric Sciences, where I wound up working under Joanne Simpson and for over 10 years. And right about the front end of my time here, we experienced what's now known as the President's Day snowstorm, 18th through 20th February 1979. You can see as the storm spun up off the East Coast, it looked like a hurricane. It's actually a very asymmetric distribution of high clouds. It's low clouds to the south, high clouds to the north and east. But that rapid intensification, which gave us this storm, which dumped well over 20 inches of snow in that area in eastern Maryland and the Delmarva Peninsula, was not forecast. The rapid development phase of this storm was not forecast at all. If you go to the next slide, please. If we look at the sequence of surface analysis here, this is again done by Paul Cosin, we had 2 periods of snow with this. First was in that 12Z 18th of February to 0Z 19th of February as a coastal front and lower pressure was forming off the southeast coast. And we got about 4 or 5 inches of snow out of that. And then you'll see between 0Z on the 19th of February and 12Z on the 19th of February, that rapid development phase occurred. And this is when we got the very, very heavy snows here. And I can tell you that in Columbia, Maryland here, I woke up to snowfall rates of 4 to 5 inches an hour for 2 to 3 hours. It was really incredible. That rapid development phase was not predicted. In fact, right around 0Z, 19th of February, the Weather Service took down the heavy snow warning that they had out. We did get enough snow out of that first period to verify a heavy snow warning. It basically said the heavy snow was over. And then after midnight is when the second batch of snow started up and really intensified quite rapidly. Next slide, please. And you can see this double period of snowfall. If you look at A and B, this is the 18th of February, where that first cloud mass came in. That's riding on the spine of a subtropical jet. There's also a lot of lifting going on with respect to that developing coastal front. But that cloud mass was shrinking as we approached 0Z on the 19th of February. And it was that signal that the forecasters used to discontinue the warnings. You see the explosion there by 12Z on the 19th of February, panel C and D. You can see that rapid development phase came about, and it was on the western edge of that cloud mass that we got the very heavy snows. Next slide, please. This was the LFM forecast that did so well for the 78 storm. You can see that that 24-hour, the 36-hour forecast from the LFM had that inverted trough, some representation of a coastal front, I guess, but really didn't develop the snow or the storm even 12 hours in advance. That low was well off the coast and moving east, and that was basically one of the main drivers was the failure of this model to hit this particular storm that drove a major effort on the research and operational community to improve these model forecasts. Okay, next. So as we worked our way into the 1980s and 90s, there was a cyclone workshop established to focus on coastal and oceanic cyclogenesis. That was NSF really pushed that under Don Johnson, who was my major professor in Wisconsin, and Peter Hobbs at the University of Washington. And then obviously all the big names became involved in these workshops. And this was done in response to that 1979 President's Day cyclone not being predicted by the operational models. We also were in the middle of this GARP experiment, Global Atmospheric Research Program, which was started in the 60s into the 70s. And from those programs, the nature of operational modeling expanded into the global domain space. This is where we actually started running our global and more sophisticated, higher resolution regional models, was in that post-Figge period in the mid-1980s. The higher resolution beta physics, use of satellite data, and significant level RAYOB data. Up until this time, and like for that LFM forecast, the models did not even use significant level RAYOB data. So the mid-80s really was another one of these important periods where the models were improved, and the results started to show. Fred Sanders, a professor at MIT, and Rich Grum, who actually worked with us in the weather service from the, I believe he joined right about the time I joined the weather service in 1989. They were doing reviews of model performances of, especially for these bigger storms, these bigger cyclones, not only over the continental US, but also over oceans. And what they showed, if you follow the sequence of their papers, was that by the early 90s, with these high resolution beta physics models, the global models and regional models, we're really starting to show the ability to predict cyclones out to 3 days in advance and beyond, including rapid and secondary cyclogenesis along the East Coast and over the ocean, with much more reliability than we had in the 1970s and into the mid-1980s. So we were starting to get bold, I would say, in the forecast community in terms of predicting these storms if the models showed them 2, 3 days in advance. If we go to the next slide, please. So this set us up for the storm of the century, as it turns out, the March 12th through 13th, 1993 storm. There's the verifying analysis. Again, this is all these analyses provided by Paul and are in our second monograph that we published in the early 2000s. You can see that this was an incredible cyclone with an incredible amount of snow produced from the southeast US, Alabama, all the way up into New England and Canada, of course. And it was predicted 5 days in advance, 5, 4, 3 days in advance. We're showing the sequence of the 60, 48, 36, 24, and 12-hour forecast, which were pretty consistent. So much so, our forecasters went out on a limb, promoting this forecast and emphasizing the impact that this storm would have on the United States. And one of the things that I was struck by, this Boston Herald front page on Saturday, it was the weather menu that they provided on their front page that really nailed what was to come. All right, this was done the morning of the storm as it affected New England and the Boston area. And you could see all the steps that were taken before the snow actually fell. So this is not just another example of a good forecast that was made of a major storm system, but it was really the response that captured my attention. At this point, I was the director of the Meteorological Operations Division at NMC, which today you would know as 3 of the national centers came out of that as we restructured NMC to NCEP, the Weather Prediction Center, Ocean Prediction Center, and a part of the Aviation Center actually came out of that. So this is really stunning, and even you notice the very top of the Boston Herald, storm threat postponed St. Patrick's Day parade. I can guarantee you that if we were wrong on this forecast, we certainly would have heard about it from the Boston area. Okay, next slide, please. So by 2000, we had this encore performance of the January 1996 blizzard, predicted 3 to 4 days in advance. And I should note that when we published the monograph in 2004 and applied this NESIS scale, there were only 2 Cat 5 storms that we came out of this attempt to develop this impact over the whole duration of the storm. There were only 2 Cat 5s, the March 93 and the January 96. And both of these storms were predicted 3 to 4 days in advance to 5 days in advance for the March storm. By late 1999, NCEP, now I'm the director of NCEP, we're rolling out our first IBM parallel processing supercomputer that went operational in mid-January 2000. We promoted the opportunities for higher resolution models, emphasized that models would be initialized with increasing number of satellite observations, warnings promised down to the county level with this higher resolution model, and we're doing all this based on our success, as we saw in the mid 1990s with these 2 major storms. So, what could go wrong, right? All right, next slide. Well, as I have learned in my career in research and in the operational world, Mother Nature tends to have the last word. So it was the 24th through 25 January 2000, which was about a week after we rolled out the computer with great fanfare, that we got blindsided by this major storm system. Now, if you look, and Steve Tracton has written this up. I don't know if he's on this or not, but Steve at the time was working in the Environmental Modeling Center promoting the use of ensemble models in short-range forecasting. We also had Zoltan Toth working in the Environmental Modeling Center promoting the use of ensemble modeling for medium-range forecasts. Well, what was interesting here in this particular time frame was we were, and to a certain extent we still are, locked into the deterministic runs of the operational models. We've made a lot of progress with ensemble modeling, and we'll show that example in 2016. But clearly in 2000, ensemble modeling was not being run operationally at that time. And you see the 7 a.m. forecast for the track of the storm up the East Coast. That's the red line. And then you see the blue line. And that's a difference coming into, level with Southern Virginia of about 100-kilometer difference. And it made all the difference. And the question is, with the deterministic runs lending itself towards the towards a more eastward solution in that track, the forecasters, did not go with this storm spreading west, as you see in the blue dashed area, with snowfall totals in the Carolinas approaching 2 feet, and blizzard conditions. We woke up the blizzard conditions in the Washington, D.C. area. And that's when, the very interesting dynamic of what went wrong started almost immediately. So this storm really caused us problems, obviously, with people's confidence in our ability to forecast them, even as late as 2000. All right. So we go to the next slide, please. This is the cartoon that appeared in Oliphant. He was a very famous cartoonist at the time. As I've said, this storm occurred 1 week after we rolled out that new computer and the new models, promise of new models that would be coming very shortly. As you see, that was captured in this cartoon. And I bring your attention to the hawk there, like, well, we were watching this thing like a hawk, and then the penguin let us know when the hawk gets here. Well, that quote from the hawk was for me. There was a very contentious news conference I was doing from the basement of my house. And I said that they were implying, the reporters' questions were implying that we were caught totally off guard by this storm. We were totally surprised by this storm. And I didn't have my public affairs person right next to me trying to answer, as I was trying to answer these questions, doing this on a phone. And I said that. So I had a copy of this cartoon provided to me, signed by Oliphant, and I hung this in my office while I was the director of the National Weather Service, so I would never make that mistake again. But obviously, this storm and our inability to capture the blizzard conditions, the heavy snowfall and blizzard conditions, even 12 to 24 hours in advance, was something that was noteworthy, not only to the larger population, but also to us. So if we go to the next slide, please. Steve brought this set of ensemble forecasts and the number of runs that would have the distribution of snowfall and the probability of that snowfall over the Carolinas and then up towards the DC area. And what it was showing was that there was a possibility that we should be paying attention to, that this storm would not just get sheared off and move off to the northeast, but could actually continue to develop and throw that heavy snow further back into the west. This was produced by what we now know as the SHREF, I believe it was just the one model component of the SHREF at the time, but it was brought to me 2 days after the event. And if we go to the next slide, please, I could tell you that that storm and what we were seeing from the short range ensembles and also from the medium range ensembles as we worked through the 2000s, like 2001, 2, and 3, we made a decision within NCEP that we would start running operational ensemble models. And that was initiated by this storm. So if we look at the second and third bullet here, the first operational implementation of what we now know as the SHREF was led by Tracton and Jundu, who was then a student of Steve Mullen at the University of Arizona. He was one of the main academic proponents of the ensemble approach. He was at the University of Arizona. Going multi-model ensemble, including both the WARF and the ADA model, I believe, was built into the SHREF, was influenced by the SAMEX experiment. And we also accelerated the JEFS, which was related to successful real-time application of Thorpex experimental work, and then went to a multi-model ensemble there as we included the Canadians and the Navy models from there. So that storm got us into the multi-model ensembles that we are using today. This also started the to and fro of forecast successes and failures through the early part of this century and the emerging predictability issues. And one of them that's particularly onerous is the curse of what I call the curse of intermittent success, where we get these high expectations after a successful forecast that sets us up for these epic outcries after a subsequent forecast failure. So we just have to keep in mind that even today, and we'll cover this with some of the opportunities we have, these forecast failures are as much related to predictability issues as they are to model issues. But nevertheless, this whole thing of having these successes and then failures has led to this, in part, has led to this GFS Euro debate within the research and academic communities. And I say it's based mostly and then almost entirely on the deterministic model runs, while I can say the operational forecasters are increasingly using ensembles based on this, what we now call a seamless suite of operational models. If we go to the next slide, please. So the seamless suite is this set of models that takes us from longer range forecasts that we make operationally now within the Weather Service for the seasonal forecast, monthly forecast, weeks 2, 3, and 4. You can see that we go all the way down into the week, days, and hours. Theoretically, forecast uncertainty should decrease as you get closer to the event, and for the most part, it does. The point I want to make with this slide is what we have outlined in green here are all ensemble model systems now that are running within this seamless suite. And most of these are multi-model ensembles. And these are the basis for the forecasting that we're doing today. Okay, next, please. But it's not just the forecast. The Weather Service also created a winter weather desk in 2001 to provide a place where the forecasters could discuss, could work through the uncertainties of these forecasts. We spun this desk up based on a proposal out of Eastern Region, and it quickly grew into a more national asset, I would say, for the forecast process. Another interesting aspect of this is that it wrapped its arms around its probability forecast right from the get-go, so that there were probabilities given for greater than 2 inches, greater than 4 inches. What the most likely was, this type of thinking, it was baked right into the winter weather desk right at the beginning. And there was also work going on in local forecast offices at this time, like Sterling, the office also near Penn State. We're working on a more probabilistic approach. Rich Grum had actually moved to the office up by Penn State and became one of the leaders in terms of providing and diagnosing off of the ensemble forecast systems. But there's also this collaborative forecasting that's needed. There's a collaborative forecast process that's being worked through within the Weather Service and outreach to the larger enterprise as well. There's science. They now have workshops during the year, and then the event reviews, and then there's messaging and outreach through social media. This is all being built now through this Winter Weather Service program, which was established in 2014. It's being run much like the way the hurricane program is run, where you review what can you improve more rapidly, apply to the next season, or what's going to take multiple seasons to affect a change. All this now is being worked through. All right, next. But again, is that enough? And the answer is no. We've found over this last decade that we have to go beyond the forecast in warnings to build a weather-ready nation. And this is basically being done through what we call impact-based decision support services, this connecting with through national security and public safety officials through this interaction with them well before we practice with them, during and after events, to improve our messaging and our forecasts that meet their key decision points well in advance of these events, so that they can get communities ready for and respond to these events as they approach. If we go to the next slide, please. So this is what impact-based decision support services are. Of course, it's all based on best forecasted warning processes in the world. We establish relationships. We know partner needs. We practice with them. We work together. We build the trust so that when these events arise, we've been working with these folks at every government level, federal, state, and local, so that they are ready for and respond to these events to ensure community resilience. And we're seeing the impact of this across a whole host of extreme events that this country experiences. Go to the next slide, please. So this has become so important to us within the Weather Service. Before I left as its director, the Executive Council, with the field support, it incorporated the provision of impact-based decision support services into the mission statement. It's not just physical science anymore. It's the physical social science connection now that's really important, because in terms of getting people to respond, you're really dealing with human factors and risk assessments that need to be addressed to get the right response for public safety and recovery. Okay, next, please. So let's bring this all together for the 22nd, 24th January 2016 Northeast blizzard. That storm, well, it did occur, and it was forecast well in advance. It also ranks right up there now as the fourth most impactful storm within the Northeast corridor. And those are the NESA scores and its ranking. Okay, next, please. And it's right up there with the 61 storm, the February 61 storm, which got me interested in meteorology in the first place. So here's the total snowfall for that storm, up to 3 feet, pretty close to DC, just north and west of DC, did receive up to 3 feet of snow. And of course, it affected Philadelphia and New York City as well, and clipped the southeast part of New England. Okay, next slide, please. This is the analysis from 23rd into through the 23rd, 6Z, 12Z, 18Z, 0Z. I think Paul produced the analysis, Paul Cosin, on the 12Z and 0Z maps, if I got that right. you can see that this storm got locked in just off the Virginia coast during the day. And as we woke up to this intense storm at 12Z, we had another 12 hours to go, as it turns out, of heavy snowfall in that area. And the storm was able to get just far enough north to clip New York City and Long Island with up over close to up in some areas over 2 feet of snow as well. So really an incredible storm system. Okay, next, please. So in predicting this storm, it was a forecast success. If we go through the next slide, please. Should just note, this is a 7-day sequence of the GFS. That was the first storm at the beginning of the week that went off the coast. This next event was about a ½ inch to 1 inch of snow that fell during the evening rush hour over Washington and crippled Washington, D.C. And then we got the big one that was being forecast to come in. And what was really phenomenal about this particular storm was that day 7, 6, 5, 4, 3, 2, 1, as we approached the event, the models were very, very consistent in this storm. And there were differences, though, if you notice, and we'll just, this last one coming in here, the earlier forecast had the snow spreading too far north, as it turns out. So there were parts about this forecast that provided challenges, especially with respect to the northern boundary. Okay, next, please. But, you know, the forecasters, using all the models and the ensembles, started advertising this potential on day 7. You see day 5, day 3. Between days 5 and 3, a slower movement of the storm was being predicted. And then days 2 and 1 were basically, we were locked on with that and where the heavy snow would be. And then you see again the analysis of that storm. Okay, next, please. And if we look at the watches and warnings that were issued, the watches were in white, warnings are in red, advisories in purple. You can see that we certainly captured the area of most significant precipitation with this. And then the advisories had the lighter precipitation on the northern edge, but a very, very sharp boundary that really posed challenges right up to 12 hours before the event in terms of the northern extent of the snow. A really remarkable performance, as you can all see here. All right, next, please. I have to throw in a couple jets. This is what I did a lot of my research on, and it is a very important signal that differentiates these heavy snows along the coastal domain space versus the snow that occurs more inland with the changeover of the rain along the coast. You need this double jet pattern, and for those not familiar, that circular orange lines in the exit region of the jet cutting across the southeast US is a representation of an indirect circulation. And that lower part of it is, it's within that lower part of the indirect circulation that the low level jet forms that really brings the moisture flux into these storms that gives you the heavy precipitation. The direct circulation in the entrance region of the northern jet has a lower branch that really works to lock in the cold area. That ageostrophic component is an important part, for example, even from a cold air damming perspective, east of the Appalachian Mountains, you need an ageostrophic component of the wind to lock that cold air in. So it's this double pattern that locks the cold air in and gets the moisture flux coming in over the top of it that gives you the heavy snow from the mid-Atlantic region all the way up to Long Island and southern New England. If you go to the next slide, please. And this is, that right side just shows, you know, the low-level jet coming in over the top of the cold, dry air. These figures are in the monograph that Paul and I put together. So, all right, next. So I show that because that pattern and the cookbook, the 7 steps that you need for the Northeast storm was highlighted on the Weather Channel. Prior to the storm, Tom Niziol, the winter weather expert, spent some time going over the model forecast to show that they were getting the right answer for the right physical reasons. So this is a 54-hour forecast from the NAM, the North American model. And you can see 300 millibars, there's a double jet. You got one off the Carolina coast, one over New England. If you go over to the right at 850 millibars, there's 70 knot winds in the exit region of the jet to the exit region of the southern jet, looping in with tremendous moisture, and that's the vertical motion field and moisture at 700 millibar levels. And there's your 6-hour precipitation that verifies at that time. And it's with that kind of pattern that you can get the that kind of precip, even as that cold air is getting locked in to the north and east of that low-level jet. Okay, so, you know, and it was pretty amazing, I got to tell you, to see the Weather Channel go through something that we worked on in the research world as a cookbook to show and to add confidence to the model forecast that they were getting it for the right reasons. All right, next. But the ensembles were absolutely essential here as well. You can see this is from day 3, 2, and 1. Part of the forecast issue was how far north was that coastal low going to get? And by day 2, we were seeing this turn to the right, so that northern boundary issue really loomed large for us 2 and 1 days in advance. And you can see the observed low tracks. There was this turn to the right. And I just want to assure you that without the ensembles, I think we would have been in trouble with this storm, perhaps over forecasting further north and east based on individual model runs that were still trying to get it up along the coast. Okay, next. The probabilities that went out reflect this. 4 days prior and 48, with this 48-hour snowfall potential of heavy snow, you can see that the Mid-Atlantic has very high probabilities 4, 3, and 2 days prior, but not so much over New York and Long Island. And you can also start seeing how that the heavier, the stronger probabilities, the higher probabilities are really getting funneled into the New York City, Long Island area, even as they were at day 2. If you go to the next slide, please. So 24-hour probability greater than 12 inches now issued Wednesday night, Thursday night, and Friday night. Friday night was when the snow was really kicking in the middle Atlantic region. It wasn't until the Friday night, Friday evening runs that we were issuing these higher probabilities over New York and Long Island, and then that little part over in southeast New England. But notice how tight that northern boundary was. Okay, so this was the way we were approaching the forecast uncertainty and working with the emergency management community. Next slide, please. I got up and did a national press briefing on Thursday. The storm really, there was no snow until Friday. So this is the day before the snow, and did the media interviews. And it was because the reason we took this chance, and this is still a risk. Things still could go wrong, but there were a lot of people on social media discounting the likelihood of this storm and that we were overhyping the storm. And we recognized this as a very dangerous situation for millions of people. This type of blizzard in the old days when there was no forecast capabilities used to kill people. This storm had the capability of really doing harm to people, not only from a snowfall perspective, but also from a coastal perspective. We'll go to the next slide, please. So just lay out a TikTok here from the 15th to the 18th to show terms of connecting all the pieces, how we were working behind the scenes with government officials at every level of government up and down the East Coast. We were doing briefing the partners on the potential for the storm, the 15th to the 18th of January. Confidence was increasing on the 19th. The partner coordination briefings, media interviews started. On the 20th, the partner coordination briefings really took on a greater sense of urgency. And you can see the watches now being issued, media interviews. What's really remarkable here is on the 21st, you see all those states with the state of emergency, blizzard warnings were issued, coastal impacts emphasized. And then on the 22nd, as the snow started on Friday, we upped the game for New York City. We actually got them into the blizzard warning and made that adjustment on the evening on the 22nd. They were in a ready, set, go mode, and they definitely went with, flights canceled, roads were being closed. The airlines, of course, started adjusting in the 21st timeframe, and people were ready for this blizzard. We go to the next slide, please. Just want to show the coastal aspect of this, at which we emphasize the maximum wind gust, nearing hurricane force winds, which were actually observed in the coastal areas of Delaware and Maryland, the wave heights, the coastal flooding, all of the above. So go to the next slide, please. So to give an indication of how successful, how do you measure success? Is it just through the physical processes or through the way society responded, the way decision makers responded? There are two papers that have been written, one by Lazo et al. In BAMS, one by Harsteman et al. In the Journal of Emergency Management. I recommend you folks reading these in terms of the value of IDSS and the economic value of a forecast and IDSS pulled together. If you look at the Long Island Express with the 2013 storm, where we attempted to, we forecast the snow changing the rain, and there was warnings put out that the snow, rain changing the snow on Long Island, that when it changed over to snow, it would change over and be hard, that you shouldn't wait to see the snow outside your window. But the systematic working with all levels of government was not in place at that time. So there's a situation where it was a relatively good forecast, but no systematic IDSS across all agencies, all government levels. You compare that with the 2016 storm, we did have the IDSS in full bloom with the folks, the state and city governments. And you see the Long Island Expressway there is just absent. Well, they closed. Right? This is 2.5 feet of snow that then got cleared in 18 hours versus the 3 days that it took to clear the expressway in 2013. The Pennsylvania Turnpike was not connected into the Weather Service in the way that the New York State was at the time. The state of Pennsylvania had a review, and they are systematically connected with us in a much better way now. But there, again, on that northern boundary and the adjustments that were made, that part of the Pennsylvania Turnpike got hit pretty hard. Those people were stranded for up to 3 days. So that worked very well. And then if you look within the city itself, 2010, there was a blizzard right after Christmas where we adjusted the forecast, but we hadn't been working with the city officials during the Christmas holidays. A lot of people were off, right? And it just didn't work. And there's your stranded buses and cars and gridlock for about 3 days in New York City versus downtown Brooklyn in 2016 that they were able to clear up within a day. So this was a big success story. And it's something that not only does the Weather Service have responsibilities for this, but the entire enterprise is working together on this weather ready nation in working with their customers, the people who work off their forecast, as we all work towards a consistent, accurate forecast and interaction well ahead of the storms, that communities have time to prepare and be ready and responsive to them. Okay, next, please. Okay, so research opportunities and challenges. There's still a lot of problems to solve. If we go to the next slide, please. You know, I've been touting the ensembles. Well, we got into March 2017 and the ensembles were showing a systematic shift to the west of the track of a low and converging in that area, well, to the east of New Jersey. Well, even from the forecast 12 hours before, they were all too far east, and the surface low cut right up across Long Island. Really made it for a bad day for our coastal snow becoming coastal rain. Okay, so still work to do. In March 2018, I know, and look, I too believe that the European Center model is an incredible modeling system, but there are certain situations where it has issues, and it's another reason not to rely on one model or just the deterministic run. But in this case, for a snow event that was going to start during the evening, the 12Z model run had an overdevelopment and put down 24 to 25 inches of snow around Washington, D.C. And I can tell you that the media and even our own forecasters during that afternoon leading up had some really intense discussions and soul searching as to whether to go with the Euro or not. They didn't. They stuck with the forecast process that they've been working with. But automated systems that are derived directly from individual model runs did suffer. Okay, so I just want to point out that the predictability and prediction issues, which the National Academy of Sciences did a report on in the June from a workshop in June of 2020, there's still a lot of predictability and prediction issues that we need to deal with. Okay, next, please. And the last I'll just note here is I did do gravity wave research in my research career. This is a storm that was written up by Russ Schneider in 1990, a major cyclone that was moving from southwest to northeast in the Central Plains, where there was also a gravity wave moving from southwest to northeast that moved through the low during its rapid development phase. So if you look at Rockford, Illinois, that pressure trace that dives down is a gravity wave signal. And I can tell that because there's a very strong winds right at the trough, the base of the trough. Well, if you look at the Chicago one, this is even more illuminating. So the gravity wave passed through the center of the low as it was developing rapidly in central Illinois, and then moved up over Chicago. So you see that very strong pressure fall and very strong winds. Well, with intense snowfall rates as well coming out of this. But there's your passage of the synoptic low that came through several hours later, and you can see that rotation of the wind and actually a decrease in the wind speed as you got near the center of the low. So what's the rapid development phase? Is it Sutcliffe self-development? Is it quasi-geostrophic? Is it gravity waves? Or is it all of the above? I think it could be all of the above, but there's a lot more research that needs to be done with that. And by the way, we saw a gravity wave pass through the 2016 storm off the coast with 75 knot winds associated with it at Ocean City, Maryland. Okay, so this is not just a one-off kind of process that we have to consider. It's something that could be fundamentally important to these storm systems and our ability to model and forecast them accurately. Okay, next, please. So I know I'm running perhaps a little long here, but I just want to note that I want to go back to my roots too. I've never lost this deep, and I would call it spiritual joy of a snowstorm throughout my life. So we go to the next slide, please. But I tell you, even with this storm, remember that red sky in the morning, sailor take warning. This is the sunrise, if we can get this. Hopefully. maybe not. Yeah, here we go. This was the sunrise of that Friday morning as I drove to work for a half day of work just before the storm was coming in. Absolutely spectacular. And I saw this as I was driving to work, as I looked over my left shoulder, driving down to Silver Spring, and I saw this incredible red sky. And I thought back to my father back from the 1961 storm when I first heard this, and thought, we're in. All right, if we go to the next slide, please. So this is what being in means. This was the evening of Saturday outside my house. That's the backyard on the left and the front yard, which I had shoveled once in the morning and then figured I better just let it cave in. But that's about 29 inches of snow drifted up to about almost 3 feet there on the left. Tabletop snow, as they like to call it here, that we occasionally get. But just an amazing scene, and just actually peaceful when I was out walking around in it. Okay, next slide, please. But I'm not alone. This review of Thoreau's workbook came out and was written up, and Atlantic reviewed that. And you know, it's as a scientist, Thoreau had to get this balance between his sense of wonder and his ability to record the factual details. Okay, but he recognized this as the daily balancing act between recording the scrupulous observations of nature and expressing sheer joy at the beauty of it all. So I felt like we're not alone in this, and it does trace back to a number of our founding fathers, by the way. If you read the journals from Thomas Jefferson and Ben Franklin and even John Adams, they were just amazed by these storm systems. All right, next, please. And I think this is a true statement, something I've come to appreciate during my career, that, you know, what gets you to come to work every morning, you love what you do. And I can just tell you that I certainly had that sense of the weather and our ability now to, you know, have a better understanding of it, but to predict it and react to it, and yet still appreciate what we're observing, what's happening right before our eyes in these amazing snowstorms. Okay, next, please. But it's not just not us; it's the poets throughout our nation's history. The sun that brief December day, rose cheerless over hills of gray, and darkly circled gave at noon a satellite and waning moon. And that slow tracing down the thickening sky, which I noted on the 61 storm, its mute and ominous prophecy, a portent seeming less than threat, it sank from sight before it set. How many times have you just keep on watching that sun disappear before you in late afternoon, just before the snow hits? All right, every time that happens here, I think of this poem. And the next poem from Mary Oliver will be something. By the way, Paul Kosin put that poem in volume 1 of our monograph. As we are now starting our work on volume 3, this is the poem that really has caught my attention from Mary Oliver. And again, there is something about a snow-laden sky in winter in the late afternoon. And then you just work through this poem where you wander slowly. The top column is stanza 3, 4, wander on slowly like the still unhurried wind, waiting as for a gift. And then for the snow to begin, which it does at first casually, then irrepressibly. That was the afternoon of the 23rd of January. Okay, right here. That's what I was experiencing as that storm kicked up. And that middle stanza at the to the right column, which is faithful beyond all our expression of faith, our deepest prayers, don't worry, sooner or later I'll be home. You know, people do have this deep spiritual connections with nature. And I would argue that the snowstorm is one of those avenues that allow us to happen. Okay, next slide, please. So in summary, tremendous progress being made in our understanding and prediction capabilities of rapid cyclogenesis and snowstorms, but challenges remain, and even and especially in the short range. Don't take anything for granted. The second one, the snowstorms are really mesoscale phenomena. We can wait for these storms now for 5 days, and it all occurs in 12 to 18 hours, and the heaviest snow occurs in 2 to 3 hours, and thunder snow occurs in 1 to 2 hours, right? I mean, it's wrapped in this synoptic scale lore, but we need to account for the entire spectrum of this mass and momentum adjustment from the global to synoptic to mesoscales to fully understand and be able to predict these storms. We need to address all scales down to the local scale for mesoscale prediction and warning as it's related to the impact-based decision support services, which are now provided at all levels of government. But most decisions in this country are for public safety are made at the local levels. So you really have to have this spectrum in a consistent way, this spectrum of information be brought down to the local level so that they're all working in a consistent way, across the emergency management community. And with all of this, physical and social science, I would just note that we shouldn't lose the wonder of it all. Remember that the passion and spiritual joy we all feel anticipating and experiencing snowstorms is what got us here in the first place. So I thank you. These are the monograph. They're available through the AMS bookstore and online retailers. I should just note for the record that neither Paul Kosin nor I receive a dime for these books. They were all written while we were members of the executive branch of the federal government and done with resources from the federal government. So we don't make any money on this. It's all goes to the AMS and whoever they're connected with now through their outreach through other retailers. So I thank you much for your attention and appreciate your interest in what we do. Thank you.
Thank you very much, Dr. Uccellini. Do you have any time for questions? I want to be respectful of your time here.
Sure.
I got a couple questions coming in. One from John Manabianco says, a fantastic nearly half-century historical perspective. If you could speculate on the next 50 years, what do you think a person giving such a presentation in about 2070 might have to say?
I think they might start off the presentation with a scene from Back to the Future Part 2, where Doc gets into looks at his watch and gets into the car before the rain shower hits. That might be possible there. But remember, he did that in '85 with the expectation that it would be happening by now. And, we still got work to do. But it's very clear that from a forecasting point of view and our abilities to not only connect with decision make, but working as a partnership with this physical and social science, that we are getting into decision making in ways now that are really going to, I think, improve our abilities to get the right responses we want. And we'll I think we'll be seeing that by within 20, 30, 40, 50 years. So yes, but I still feel that there are nonlinear aspects of intense extreme weather events within this warming climate. They are getting more intense. Whether it's these intense snowfalls, very intense rainfall rates, in flash flooding. We're seeing flash flooding in ways that like the Ellicott City floods that we have never seen before. They're not the mainstream river flooding. It's coming from the top of the hill down. A number of factors in there. There's just still something that I would be cautious as we work our way through this to be respectful of the fact that Mother Nature has its ways of throwing curveballs at us. So, but we're certainly on a road to, I think, great advances from a forecast and point of view, working collaboratively within an enterprise that's respected around the world as the best weather enterprise. That's public-private, academic connectivity in the world. I think we'll be in good hands as we move forward.
All right, and if you have time for one more question, this comes from Paul Joseph. He asks, how important are local meteorologists in understanding local influences of a pending snowstorm, and how can local forecasters improve upon computer models?
Well, the local forecasting it's still very important. There are aspects to it, and sustaining a situational awareness of those changes are going to be incredibly important. I think I don't want to take away from the importance of the local, but I emphasize in the summary as the global synoptic to mesoscale connectivity, and the more regional to national forecasting will really help that along. Those people are not going to have the situational awareness that the locals will have. I mean, that's what I still see. And so it's really going to be a collaborative forecast process, people working together that we're already seeing in the Weather Service and we're already seeing in the enterprise. That's going to be extremely important, because I can tell you that when we talk to the emergency management community or people responsible for public safety, their number one requirement is consistency. They don't want a whole bunch of different forecasts that they don't know what to do, okay? So we have to work collaboratively to ensure that we're bringing our strengths to the table and that we all agree on how to move forward, because we should be measured by the decisions being made for communities to be ready for and respond to the oncoming event. And then we can argue about what forecast element needs to be improved later. But the point is, a collaborative forecast process, bringing a consistent message to those that are actually on the ground, saving lives, right, and mitigating property loss, is what's the key measure of success that we should be working towards.
Well, fantastic. Thank you so much, Dr. Ushley, for everything and for your time for this presentation today. I think that's all the time we've got. For those of you looking for where this recording is going to be, it will be available after it's uploaded at amsweatherband.org. I want to thank you all for coming today to this presentation. Thank you, Dr. Uccellini.
Okay, thank you all. Bye-bye.